Pleased to see you all. My name is Peter Boncz, and I'm from the CWI, the Dutch Center for Computer Science and Mathematics Research. And I'm indeed on sabbatical in a company called MotherDuck. Hey, Stefan. Yeah. So let's click on this. Yeah, so I'm going to actually kind of, because we are here at the LDBC TUC meeting, so I'm going to completely fast forward through the entire graph data management section here. So you all know, there's graphs around. We want to do pattern matching, path finding, and relational operators on these things. And yes, if you have graphs, then you can store these as tables. The graph is G is v, e, a vertex table v and an edge table e, so you can of course represent that relationally. And you can even write relational queries doing graphs. Like here I'm writing a query that's counting all the people that Bob knows who follow him indirectly over follows graph. But you can see that this graph, this SQL query is rather nasty. Okay, and what we have had in the past, lots of a whole wave of graph database systems, Neo4j being the most widely adopted one among them. But of course, also as we have listened to the whole class of Sparkle systems, also graph systems, they have a lot of different query languages, and that's a Tower of Babel problem that was eventually tackled by having a lot of standards, So if you have X query languages, then you can have X+1 or even X+2 query languages now, because the ISO committee in liaison with LDBC started working on ISO committee that's actually doing a SQL, started working on SQL-PGQ, which is now this the adopted standard extension of SQL adopted in the 2023 version of SQL to do a property graph query, PGQ. And that is the X+1, and there is also X+2 since recently, because now there is the native query language GQL, which is very similar to PGQ in its core functionality, but it's a native query language that can also do updates. Anyway, I'm talking about SQL-PGQ here in this talk, because I'm talking about the state of DuckPGQ, and we'll come to what that is. But SQL-PGQ, the language, what it allows you to do is to define over an existing schema that you have in a relational database, where you have a table V with vertices and a table E with edges. A table E with edges would be something like a connecting table that causes an end-to-end join, essentially. And these occur quite often. But now you can kind of create a new sort of view, which is called the property graph, that says, okay, these tables together, they form a property graph. So you have kind of a view that actually does not duplicate necessarily the data, but it points to data that you already had in SQL tables, in relational tables. But you can now have property graph kind of functionality over it. And the property graph, as what previous speakers have already memorized, is a directed graph where you have vertices and edges, and on these vertices and edges you can have properties being key value pairs, essentially. But in the case of the relational extension, the properties are essentially the columns of the tables. So the key would be the column name, and the value being the value in the table under that column. Okay, so now you have these views where you can view your tables as graphs, and then you get query language or sub-language where you can do things like match and path finding. So match being pattern matching, path finding is finding paths over these graphs. And eventually this fits into SQL in that this sub-language will return a table which is then visible in PGQ as a graph table result. And a graph table results can occur in the from clause. So basically, your graph query gives back a tabular result, and you can join it with other relational tables or with other graph table results. So here is an example. So we had this tabular schema. We had actually two kinds of vertices here, the city and the person. Yeah, so the types are basically tied in the property graph model to labels. So you would have labels on these edges and vertices. So the vertices here have labels city or person, and the edges in this case have lives in or follows. And yeah, follows being a proper edge table, the create table follows, and lives in actually being some kind of foreign key relationship. Then you have a one-to-n join, not an end-to-end join. It's also possible. And with those extensions, then you can formulate the monster query in a much shorter way by using syntax that is reminiscent of Cyber, the query language of Neo4j. And you have this like ASCII art notation in there, where around brackets are vertices and square brackets are edges, and you can have an arrow with a star, which is a clean star, over these edges. Okay, so it becomes shorter. Yeah, it's nice. It's nice to have another standard, of course. Now that we have this, and it can do pattern matching. It can do path finding, and it can also do your good old relational operators. You can have filters, you can have aggregations, all that. So it's great. So now we have this new query language. But having a standard is only one thing. It only comes to life if there are actually systems that implement this. And if that doesn't happen in a reasonable time, this standard will be forgotten and it will kind of disappear. Currently, the only vendor that's really out there with some support for PGQ, okay, we are only 1 year, less than 1 year maybe, no, we are 1 year in Oracle currently. They don't support everything, but they have at least an implementation. But it's still not very convincing. So we were thinking about having a PGQ implementation in DuckDB. DuckDB being a database system that is that originates from the CWI, from our group. Was originally created by Hannes Mueijs and Mark Raasveld. And what they do, or what they want to achieve, was to create a database system that was suited for data scientists. Because they were observing that, well, data science, being the most sexy profession at some point, before problem generation came into our lives, was actually largely bypassing database systems. So people in data science were using pandas mostly, and hating database systems because clunkiness, difficult to install, mismatch with what they really wanted to do. So to address this issue, Mark and Hannes actually worked a lot with data scientists, and they came up with this concept of an embedded analytics database system. And that means something that can really run in your Python environment, in your Jupyter notebooks, and that would be able to communicate results without actually copying them by running actually in the same address space as where your data mining or machine learning library also runs. Okay, so that really took off, and now this DuckDB has more than 2 million downloads per month, lots of stars, and this has been increasing a lot. So DuckDB is storming into the top 100 of the DB engines ranking. Still not top 10, but it's steadily advancing. So it's by far the most successful database system that the CWI has ever created, with millions of users. And well, there is a spin-off that's currently is focused on making DuckDB successful in the open source space in the most broad sense of the word, and that's called this spin-off company is called DuckDB Labs, and that's where Mark and Hannes spend now their time mostly. But there's also this MotherDuck. MotherDuck is a startup that was kind of co-created by DuckDB Labs that is going to put DuckDB in the cloud. So that's where I'm doing my sabbatical already for 1.5 years. Really enjoying myself, doing some hacking, but I'm not just wasting time talking to people, not doing PRs. Sorry. But okay, I'm not going to talk about MotherDuck, but that's where I'm doing my stuff. So what do we actually do? Also in MotherDuck, but also in DuckPGQ, we are using the extensibility of DuckDB. So here you see a schema of how DuckDB internally executes queries. So queries go through 4 stages. First, they are parsed. So that means that the SQL text is parsed into a so-called syntax tree. And the second step is kind of binding, where DuckDB will consult the catalog and do lookups. Do the tables exist? Do the columns exist? Are the types correct? Is there a semantic error? If that all succeeds, then you get a so-called logical relational algebra plan. And that is then optimized. The operators are maybe reordered. And finally, this is executed. By the way, how am I on time? Yeah, but how many minutes have I already wasted talking about?
Halfway, so 10 minutes.
Oh, yeah, okay, so I should speed up. Executed, okay. So all these stages are extensible. Of course, SQLPGQ is a language extension, so you need a parser extension. Parsers are actually famously not extensible, because something like Bison generates a state machine. And if you change something in the grammar, the entire state machine changes. So notoriously, you cannot really extend parsers. Yet DuckDB allows you to extend parsers. And what that means is that when you generate a syntax error, then it will check its extension modules if they register their own parser, and it will call them one by one until one of those extensions actually is able to parse this query. Actually, it's even more intricate, because the module will actually say it looks like something that's mine, because you also want the parser to generate sensible error messages. But it could also be that it says, it looks like PGQ, but so I will parse it, but it's actually incorrect, so only generate a PGQ error message. Works, okay. So we did these extensions to the parser. We registered the PGQ extension, and then we also bind it. So we look up. But this means that we look up when somebody actually defines the property graph view, okay, and all that is correct. And eventually then we generate a logical algebra tree. And that's actually where DuckPGQ initially ends. So it just remaps DuckPGQ into kind of relational algebra, and then it's back to DuckDB. It's like back to plain DuckDB. And this is described in this CIDR 2023 paper. And I should, of course, say that this presentation I had on the first slide, but I forgot to say that Daniel ten Voorde is my PhD student who is working on this. And but he is not here, so that's why I'm standing in. Okay, so yeah. So what's actually, there's gory details here, because the DuckDB parser extensions are actually intended for simple parser extension. Like MotherDuck has something like create database or attach database, and these are single statement extensions. You can ask Stephanie here in front all about that, DuckDB parser extension or for MotherDuck. That's a relatively simple extension. Sorry, Stephanie. But what we have to do here is, this is SQLPGQ is a superset of SQL. So it's not a standalone statement that you can parse. It is the complete SQL plus more. So I actually do need to make a complete new parser. And we are exploiting the fact that if you create an extension module, now fasten your seatbelts, then if you compile that, you get like a .sl, you get a library. What DuckDB does, or happens to be doing, in order to avoid linking problems, is it actually links the complete DuckDB library into your extension module. So when you use an extension, you actually have 2 copies of DuckDB, because you have DuckDB that you started from, and then you load the module, but it also has all the symbols of DuckDB. Has to be absolutely the same version, by the way. That's it. It makes a check for that. Otherwise, you know, the 2 different compiled DuckDBs are different and everything crashes. We make use of that by having a fork of DuckPGQ that has the modified parser. So when it jumps into our code, we have SQL-PGQ parser. We parse it, we rewrite it into logical plan. By the way, that tree with C++ objects must be exactly identical to the thing that the original DuckPGQ expects. Then we give that back, and then it somehow miraculously doesn't crash. So yeah, quite an adventure. Yeah. Okay, so what it does is, well, like I said, for the pattern matching, mostly it remaps pattern matching to joins. That's what you would expect in a simple approach. But for the path finding, we actually use an algorithm. Well, we use a data structure called CSR. I think I will skip explaining that to you, because if you're in this room, you probably know what the CSR is. And if not, then you can ask me afterwards. But it's a compact representation of the graph. And then it uses an algorithm called MSBFS, multi-source breadth first search. That is, was published in 2014, it will be by the tool. It is a kind of very efficient breadth first search that actually exploits SIMD instructions. So in one search, you can do 512 searches. So you can look for 512 source destination pairs in one call. And it maps these into bits of your SIMD register. Okay, the state of the graph is mapped into these bits, and that's how it accelerates searches. Yeah, and but we implemented this as a scalar UDF. It was also because we were quite new. I mean, I hadn't done my internship at MotherDuck yet. I wasn't on sabbatical yet. We didn't know that much. Scalar UDFs are relatively simple. They are just a function that you call. Okay, it's vectorized, so you get 1024 parameters instead of one, but okay. Still relatively easy to understand what it does. You just implement the function, let it do something, you return 1024 results, done. So it means we can do 1024 searches in one call. So this is something like a find path function that we created. Okay, so we actually have two extensions, so we go beyond the standard. DuckPGQ supports weighted source paths. Actually, the pathfinding support in both PGQ and GQL is still rather restricted. There is a promise to do more, but we already do more. So we can do weighted shortest path by taking into account the cost. We can also return that cost, and then you can find the lowest cost path. We also have an extension in how we define labels. So here you see something like in mask there. So this is the statement. And this allows to have some kind of integer column that kind of encodes the membership of the various labels. Because sometimes a vertex or an edge can be multiple things, like a person can be a student or a TA. It can, or all three of them at the same time, even, by setting masks. So it's relatively easy to define this and to bulk import or bulk interpret your SQL tables, where mask is just a column, and to know to which multiple labels a element belongs. So we found that when we were trying to implement the S&B benchmark, and there you have messages that are posts, that are messages or replies, and then they are in an inheritance hierarchy. And that's one of the things that you can do. Okay, so that was the state that we had last year, and the state of DuckPGQ now. Okay, so what have we been doing? We have been working a bit on GNNs, so graph neural networks. Graph neural networks do kind of graph mining, you can say, on graphs. So what we want to be able to do is we could say, okay, you have a property graph in your relation database system. Do GNN inference, for instance, on that. And vice versa. You may start with DGL, PyTorch, Geometric, which are the most popular GNN libraries. They are Python libraries. You may have an interesting graph, and then you would want to maybe store it in, or manipulate it, even or query that in DuckPGQ. And DuckPGQ has this nice zero copy functionality, and so we want to maintain that. So it should be really instantaneous that you actually use DuckDB or your Python library without actually importing or copying the data. The data should not move. So this is one thing that, that we worked on. Yeah, we also went further. Now that we know more about DuckDB, we ventured into extending the optimizer and extending the operators. So because that is how the queries, yeah, so you first do this binding and logical plan, optimizer kind of reorders it, creates a physical plan consisting of operators that you can execute. So what we have been doing, so this find path method of doing path finding as a scalar UDF has big problems in terms of parallelism. In one way, it's very easy to get parallelism because if you just have a scalar function, DuckDB will parallelize the query for you. You have no, it will do it for you. You don't even see it. You will just have a lot of maybe data, and the function has to be calculated on all these tuples, and it will just farm this out. Morsel wise, but what is a morsel in DuckDB? The unit of parallelism is 120,000 tuples. So that would mean that only if you have more than 120,000 source destination pairs where you want to find a path for, you would get more than one thread. Okay, so there are use cases for that. If you want to find paths for all your data, the shortest path for all your data, then that would work. But if you have fewer source destination pairs, you would get single-threaded execution, and that's not so nice. So we have been now working on actually creating a pathfinding operator. And that operator needs to use a very different parallelism model. So it needs to schedule its own threads in DuckDB. There is a concept called events, DuckDB events. When DuckDB executes operators, it can actually coordinate the work between multiple threads in epochs that it calls events. And here events will be, because we do breadth first searches, is advancing the frontier one step. And so that's also a barrier where all threads then will have to stop, wait for each other. Okay, and then the next event comes, and the next event comes, and the next event comes. And here with that, you can parallelize the pathfinding in a different way, namely on the graph. You can say every thread takes ranges of the graph and advances the BFS in those ranges. So you can do fine-grained parallelism in search. There's also additional opportunities because now you have to create a source and a sink. Source is like where the data comes into this operator. The sink is where you materialize the output of your operator. In the source, you can do duplication of source and destination. If you have to search multiple times for the same source and destination, you can already detect this and filter out and only do the work for the unique combination of source and destination. That can also save a lot of work. Actually, for breadth first search, you will actually go to all the destinations. So even if you see that a single source repeats, maybe with different destinations, you can still do it in a single breadth first search. So, and vice versa, you could also turn everything around. If you see that the duplications happen in destination, you can revert all the edges and do the same optimization. So it gives you some additional optimization opportunities. And finally, we are also working on factorized query processing. So it starts kind of really low level. DuckDB's join is a hash join, and it uses a bucket-chained hash table. And in a bucket-chained hash table, you have chains for the collisions, but also for the duplicates. And it's actually mixed. So you have these buckets, and if something is in a chain, it can be for two reasons. Either because the key happens multiple times. So yeah, you have multiple occurrences of the key. Therefore, they have to go into the chain. Or you actually were unlucky and you had a hash conflict and two different keys hashed on the same bucket. We changed this actually to having chains only for the duplicates. This is actually also faster for joins. So hopefully this will be merged soon in DuckDB. We'll make the join a bit faster with this new hash table. But why we were doing that low-level stuff is because of this paper. There is a cider paper called the 3D hash join. And the 3D hash join proposes to, in a hash lookup, to not immediately generate the results if you find something in the hash table, but rather to emit a pointer into the hash table that points to the chain, to the list of all the hits in this case. So this allows you to delay kind of blowing up a result. And then hopefully maybe a filter comes in or an aggregation comes in that makes the intermediate results smaller before you have to expand the list. Because you can have in a graph query where the list contains all your friends, you can have like hundreds of friends, or some people even have millions of friends. So not expanding the intermediate result makes sense. And that actually brings us into a world where now so some of these ideas, or actually most of these ideas, have been appearing in various works, like Semi Sayiloglu's group has done a lot of work. There is interesting work in systems even. The TUM has done interesting work. But now in DuckDB, we have this phenomenon of a join not materializing all the results, but emitting a hit list or a pointer to a chain somewhere in the hash table that it created for the hash join. And it has three kinds of opportunities that we now see. So you can exploit these hit lists in aggregation, and you get factorized aggregation opportunities. You can, if you have a hit list and those hit lists are actually foreign keys, and you have to join with those into another join, then you can factorize on the join, so you get factorized joins. And sometimes if you have certain shapes, specifically if you have cycles, and you close the cycle, that's kind of known to reduce the amount of intermediate results dramatically, then you have an opportunity for deploying worst-case optimal join algorithms. That's where we are currently working most on. I have a student called, well, he is a master student, Paul Gross, and he is doing his master thesis on this, and this looks really promising. And the really novel part of all of this is that in DuckDB, typically users do not give us statistics. In data science, you often have data lakes. There is no opportunity to do analyze tables, so you actually get very little metadata to base query optimization on. And one of the biggest challenges actually in these factorized and worst case optimal join systems is knowing when to deploy these algorithms and when not. And this is maybe even the hardest problem of all. So our idea here is to delay the decisions until the hash tables have been built. Because after the hash tables have been built in a join plan, you have seen all the data, and you have very accurate statistics then on what the data looks like. Data distributions and the explosion factors. And so the idea is to actually make a dynamic adaptive decision to go for a worst case optimal join or not. And that would be a first in a database system. So I'm probably over time. So because I did not skip DuckPGQ, I gave you a very, very, very quick overview of that. I talked a bit about DuckPGQ as it was released last year and described in the CIDR 2023 paper, which added parser support and had this scalar EDF approach. Some extensions, and I talked about the ongoing work, the GNN library support, better parallelism, fine-grained parallelism, and factorized query processing. We have not released that yet. What we have released is basically last year's, but it's actually up to date, so you can even get the latest version of DuckDB. DuckDB just went 1.0, and install DuckPGQ, and you will find bugs because it's still an alpha release, I would say. But we're still working on it, and we hope to get it to a less buggy state, and then we'll make noise about it. But you can already try it. It will do PGQ. So maybe that's good news for PGQ. There is one more system that actually accepts it. With that, I have to close, I suppose.